We just saw an example where we walked through carefully the execution or the invocation of a function call, a factorial, in order to see how the different scope frames were created and to help us sort of decide that in fact it will stop when it reaches a base case and return a value. But when I start trying to design code, I have to think about the same thing. How do I set it up so that I know it's actually going to stop? How do we know our recursive code is going to work? In the case of an iteration, we know that by making sure that we've got a loop invariant that changes as we go through it in order to make sure that we actually get down to a place where we hit the end test. So mult_iter terminates because b is initially positive and it decreases by 1 each time through. I've set that up by making sure I change it by 1. And so I know eventually it's got to get down to a place where it's less than 1, which is going to trigger that end clause. And I can use that to deduce that I've written code that is in fact going to terminate if I give it an appropriate set of values. What about the recursive version? Sorry, as I said, mult is called with b1 and that it has no recursive call and it stops. But how do I know that it stops in general? Well, if I call mult where b is greater than 1, it makes a recursive call with a smaller version of b. And so again, I know that eventually it must reach a call where b is equal to 1. This tells me that when I write a recursive version of a function, I need to make sure that I'm changing the parameter, in this case this value, so that I'm going to get down to that test case. That's nice, but there's another way in which in fact I could reason about my code to decide, is it going to in fact terminate or is it going to get into an infinite loop because it's going to recursively call itself over and over again. And to do that, we can use, as a little sidebar, a nice little mathematical tool called mathematical induction. Here's the idea behind induction. If I want to prove a statement that is indexed on integers, that is, it's a statement that is applied to a set of integers. If I want to prove that statement is true for all values of some parameter n, I just need to prove that it's true when n has its smallest value. For example, n is equal to 0 or 1. And then I need to prove that if it is true on an arbitrary value of n, I can also then show that it must be true for n plus 1. And with that, I can then essentially deduce mathematically that it's true for all values of n. Let me show you a little mathematical example of this. The sum of the integers for 0 up to n I claim is n times n plus 1 divided by 2. If n is 1, it says 1 times 2 over 2 is 1. If it's 2, 1 plus 2 is 3, and 2 times 3 divided by 2 is 3. You get the idea. How would I prove this is actually a true statement? Well, the proof says, take the simplest case. If n is equal to 0, what do I have? Then the left-hand side is just 0, and the right-hand side is 0 times 1 divided by 2, which is just 0. So it's true. To prove it in general, I simply assume it's true for some values, let's call it k. And then I need to show that it's true for k plus 1. So I need to show that this statement is true. Oh, but that's nice, because the left-hand side, I know that it's true for that. I just assumed that. I know that in that case, that is k times k plus 1 divided by 2. So the left-hand side is simply that, by that assumption. And if I do just a little bit of algebra, I can show that that is in fact the same as this. And I'm done. Having proved it, assuming k, therefore it's true for k plus 1, I can now say it's true for all values of n. So this formula is always true. What does that have to do with code? Well, I can do the same thing. Here, with my case of a recursive call to mult, I need to do the following. I need to show the base case is true. Will this return the right answer when b is equal to 1? Yep. Now, what about in the recursive case? I'm going to assume that my code does the right thing for smaller versions of the problem, meaning that I'm going to assume that mult returns the right answer. And in that case, I can then say on this piece of code, if it does the right thing, then this return does the right thing, because it's simply an addition. So in that case, I know it returns the right answer for a problem of size b. And by mathematical induction, my code will always do the right thing for appropriate values of a and b. Thus, induction tells me I've got code that works.